Welcome back to The Lone Engineer, your go-to destination for exploration and experiments in advanced C++ and Python. In our previous session, we talked about the intricacies of reading GPU texture data, and we began the validation process for the transmittance texture. Today, we continue our journey by exploring the actual content of the Precomputed transmittance program in WGSL. Before we embark on this coding journey, I encourage you to subscribe to this channel if you appreciate hardcore and advanced C++ or Python programming content. Also, please consider giving this episode a thumbs up if you find the information valuable. This will be greatly appreciated, as your support is always really motivating for me. As always, your insights and questions are very welcome, so feel free to share your thoughts in the comments section. And now, let's get started with this coding expedition. Alright, so we just provided a simple mechanism to be able to read the content of the texture from the GPU into a vector here using this debug read texture data function. And after that, we were just displaying some of those values after converting them to float values to see that there were actually non-zero values, so there is something ready to be validated. And we're going to continue today with the actual validation process. We are talking here about the transmittance texture, and so we can have a look at the Precomputed transmittance program here. In there, it's actually pretty simple compared to the other programs that we will discuss later on. What we're going to do is simply to get some coordinates depending on what is the current global invocation ID, and using those coordinates we're going to compute the corresponding transmittance values, which is going to be a vec3, and we're just storing this vec3 in the output texture. So everything is happening here. So that's typically one of the functions that we need to kind of duplicate on the C++ side, and this one is only used to in fact convert your fragment coordinates into what are called the R and mu coordinates in the Precomputed atmospheric scattering algorithm. Once we have the R and mu value, we call the actual function which is going to do the transmittance computation with R and mu. So this is the one here. This one is calling again another function here, and it's also using some of the atmosphere parameters themselves. So on the C++ side, we will also need to provide those atmosphere parameters, obviously, but I think we already have that in the threads, the atmosphere threads that we use to create the atmosphere model. For instance, here, if we check the threads structure, we see that there is this relay scattering value, but it's actually a vector of double values, whereas here we are probably just expecting a float value in fact. Well, no, actually, if we check the definition WLSL, we see that in the atmosphere parameters the relay scattering is a vec3. So this is now making a bit more sense. So yes, here this is a vec3. This is probably just float value, and I would expect this also to be a vec3 and this one. In any case, we should be able to retrieve all those parameters on the C++ side, so we will be able to compute exactly the same thing. And indeed, this method here is just returning a float value, and it's again using other helper functions here to perform the computation. So now let's get started and try to replicate all those WLSL functions on the C++ unit test. So I'm starting here with the implementation of this first function, and one issue that I noticed was that I need here to be able to divide a vec2 by another vec2. So I am currently extending also this vec2 class that I have to support division by vec2. So I just added those two additional functions. Next, I need to provide implementation for this converter. Now, trying to implement this helper converter, I realized that I already need this atmosphere structure. So this the list of parameters for the atmosphere. And the point is, with the threads that I'm providing to create the atmosphere model, I don't really have the atmosphere parameters out of the box. So I came to the conclusion that I also need to provide the structure, so this atmosphere parameters in C++ version here, and this one will correspond to what we have on the WGSL side. So we have it here, the atmosphere parameters, which may also contain additional helper structure, the density profile and the density profile layer. Now it means that when we call this function, we also need to provide access to the atmosphere parameters themselves. So we should provide the atmo structure here as function argument. Okay, so after a few additional changes, we now have this function which is implemented properly on our C++ side. What is different, for instance, is how you would do the selection. You can use a ternary operator here in C++, whereas with WebGPU we were using this select function. I also added a couple of helper function here, the clamp cosinus and this get unit range from texture code. Here it seems, yes, I'm still not using flop values properly, so let's fix this. And apart from that, I think we should be okay. Next, we need to continue with adding the final function here. Another thing I just realized was that for the density profile layer, so far I was using double values to store the data. As you can see here, float 64. But in fact, on the WGSL side, what I have are rather just float values, so float 32. So I really need to convert that here, and I should be using float 32 in this case also. Now, working on this function here, I realized that I also need this exponential helper function implemented for the vec3 class. This is not available out of the box here, but it was on the WGSL side. So let's add this. And now we should have all the required function implemented. And with those, we can prepare the computation that we need to build an array with the expected transmittance values. So the idea to compute the expected transmittance value is really simple. We prepare a vector like this one, and we resize this vector to be the same size as the transmittance texture itself, and we're going to write the value one by one. What we need to be careful about is to iterate in the outer loop on the row index, so starting from a given row and going higher to the latest row, and then in the inner loop we're going to iterate on the column so that basically the u-axis of the texture, while the row number is going to give you the v-axis of your texture. And inside this loop we proceed as in the WGSL shader. We're going to prepare those coordinates, which is a vec2, and we're going to call this compute transmittance function with those coordinates to produce transmittance data. So in theory we should do something like that, except that on the C++ side this function is also expecting to take the atmosphere parameters, because we don't really have that available out of the box. So it means that now I need to find a way to prepare those parameters before calling this function here. Okay, so they're working on the generation of the atmosphere parameters. As I said, we need this atmo structure to call the compute transmittance function. So we need to prepare this structure before we go into the for loops. And at first I thought I could provide just a static function to try to convert the threads that we use, so which are generated here at the top of the function. And so trying to use all those threads to generate the the atmosphere parameters here. But this actually doesn't really work, because if you look at how we generate this structure, this was done mainly in this helper function. So in this function, when we want to generate the header for the shader, we're going to prepare the atmosphere parameters as we have here. And the fact is that all the elements that we are providing here that are written as strings, but for instance here we have this toString function which is used, and this is going to convert what we have in the threads, the solar irradiance that we have in the threads, but also using the lambdas that are provided here as a function parameter. So the output will depend on what we are providing here, which means we also need to provide those lambdas here. And on top of that, if we have a look at what this toString function is doing, it's going to use the interpolate function itself, and it will use threads to access the wavelengths here. So we basically need to access the atmosphere model, or we need to provide the threads directly. For now, let's just say we don't make this a static function, and we will use the model to generate the parameters. Let's now try to complete this get parameters function. Okay, so here is the final version of this get the parameters function. I have introduced a small helper function here as a lambda, because we need to kind of provide the density profile using the available layers, density profile layers. And in the threads we only really have a vector containing a list of layers, so we don't have this density profile created. And before that I was using this density profile function here, but this one is really producing a string at the end, so not really what we need here. But apart from that, nothing very fancy. There was already this interpolate vec3 function. I mean, maybe I didn't mention that. So this one is doing this similar thing as this toString function, and in fact we could also use this function here. Let's do that. And here we are. Now the toString function will use this interpolate vec3 first, and then convert vec3 into a string. And also, yes, adding this vec3 plot constructor call. Now that we have the get parameters function, we should be able to use this in our unit test here to complete the generation of the expected data. But in fact, what we could also do here is try to monitor how long it will take to do the generation of this data on the CPU side. We already have the timer, so it's very easy to just start the timer again, perform the computation loop, and after that we will stop the timer, and this will tell you how long it took to generate all the data. And in fact, executing this code, I got this output, so a bit less than 1 second, so just good. Next step now is to actually do the comparison and see if it's really matching what we have in the GPU texture data. And actually, looking at this code, I realized that I don't really need to store the computation result in this expected vector. I could just do the comparison on the fly, because when I had transmittance data here, I could compare that to the corresponding pixel in the data vector here. So let's try that instead. Okay, so I have tried to compare what we have on the CPU and GPU, and the first test here is not very good, because the results are not matching a lot. I mean, not matching at all, I think. But if you look at what we have, it seems that on the GPU side we have kind of realistic and proper values, but on the CPU side everything we get is very, very small. So I would tend to think that there's something wrong going on the CPU side. And from here, I guess, yes, I need to investigate further and try to figure out where is the problem exactly. So let's get to it, the funny part. So the way we're going to perform the actual testing here is to proceed progressively and try to add more complexity step by step. So what we can do, for instance, here is to not compute anything for the transmittance and just take the input coordinates that we are providing before the actual computation and use that to fill the transmittance text vector here, and we do the comparison here, and at the same time we do the same thing on the shader side itself. So here you see I have commented this computation line and I just write the coordinates into transmittance, and normally if you do that you should have a match on both sides. This is what I tried here, and indeed in this case there is no problem, but that's pretty much expected because we're not doing anything complex or anything at all here. Now we're going to go one step further and try to start with what we're doing in this function and check again and again and again until we find something going differently on both sides. Let's do that. So continuing on this path, the next thing I have changed is in this function, instead of computing the actual transmittance value, I'm just trying to compute the R and U coordinates, and I'm going to return this as the final output. And I'm of course doing the same thing on the shader side. So here I'm returning a vec3 containing the R and U coordinates and a random value here, which is just 2. If I do that, I will notice that the unit tests are starting to fail now, but they are always failing for the Y coordinate, which is actually the new value and not the R coordinate. R coordinate seems to be okay, but for the new, you see that there's a mismatch. Now the mismatch itself is in fact very small, so I would say that this is not really an error. It's just that the computation is not done with the same precision, not the same architecture and everything, so it's kind of normal that you don't find exactly the same floating point values, which means I need to be a bit less strict on how I do the comparison. But yeah, maybe we could just push it a bit further before adding a different mechanism here for the comparison itself. Let's see. Next, I'm comparing the Rayleigh scattering value, no error in this case. The Me extension value, again no error, and also no error with the absorption extension value. Now let's check what we have with those compute optical length. And as could be expected, when we try to compare the compute optical length to top atmosphere boundary values, we start to get a lot of mismatches. Actually, every single value is completely different on both sides. If I comment all the integration loop that we have in the compute optical length part and just return this dx value, we'll still get a lot of mismatches for the x, y, and z coordinates, but as we can see here, the actual values are almost the same, so it's more a rounding issue or computation issue that is not really a bug here, so this is not a problem here. So we need to go deeper and figure out what's going wrong here. Next, if I return just a fixed value in the get profile density here, we'll see that the integration loop is working probably as expected. It's just again that we don't have exactly the same value, but they're close enough to consider that there's no significant difference between the two implementations. So it's somewhere here in the profile density that we have something going wrong. Let's see. I also just tried to report the altitude divided by 1000 here in the get profile density, and in this case we get similar result. The value are not the same exactly, but they're very similar, so it means that the altitude parameter that we are providing here should be okay. So it's really what's going on with the density profile itself where we have a problem apparently. Well, okay, what I just realized is when we are generating the string version for the density profile here, we're going to, okay, first insert a default profile layer if there's only one of those layers, and the thing is, then we call this one the density layer function, and when we call this one, we're not going to use the layer data directly. As you can see here, we're going to transform this a little bit. For instance, the wedge here is divided by the length unit in meters. The exponential scale is multiplied by that value. And those changes we are not reflecting currently in the get parameters function. So now I have just updated the get density profile lambda function here, so that for each layer I'm going to apply the transformation that we need using this length unit in meters variable. Alright, and with this change, it seems that the values that we get now are pretty close again while performing the complete transmittance computation. They're not exactly the same, and it seems that sometimes they're drifting a bit far away. Like for instance, if you look at this, you can see 0, 2, 4, 0, and then you compare that to 0, 2, 4, 1, which is kind of noticeably large already. But I'm thinking it could be because I'm mixing some type of value here between float 32 and float 64, so I'm going to double check that, and maybe I will find a way to improve the consistency between the two implementations. But it's already pretty satisfying, and I guess, yes, we can consider that as a proper validation for the unit test. I just need to accept the differences now, so we're going to modify that. So the first thing I have changed to try to improve a little bit on the precision of the computation was to not perform the multiplication by this length unit in meters afterwards when we already have created the layer structure, and instead we could use the initial value here, do the multiplication producing float 64-bit, and then convert that to a float 32 afterwards. But this didn't really change that much the differences from my perspective, but it was not really easy to test that, so I've also now just changed this the way we do the comparison here. So we're going to use closed fraction instead of just comparing for equality. And currently, if I use this threshold, I can get the unit test to pass properly, so that's great. But I have introduce a small modification here in the get layer, pretty large modification here in the get layer density, because I'm currently only using the constant, the layer constant term. And I think that if I use the linear term and the exponential term, I'm going to see more differences. So let's try to do that. Okay, so I have just tried to add this linear term multiplied by the altitude value, and the test is still working fine. So using the same threshold, we don't need to change that for the moment. So let's try again, adding the exponential term at this time, so the full equation here. Okay, so if we use the exponential term also, in this case we get some elements that are not matching because the difference is bigger than before. So yeah, so this value can grow quite big, in fact, and most of the time I think it's for small transmittance values. All of them are pretty small, and that's where you can get larger differences, larger relative differences. I'm not quite sure there's anything I could do here to improve on this. I will need to maybe understand a bit better how the exponential function is working, both in the web GPU implementation and in my C++ version here. Maybe there's a difference here, and I'm not quite sure what I could do about that. So how am I going to work around this issue otherwise? Let me think a moment. Okay, so with some additional testing, I am now realizing that differences are all related to this exponential term here. If I use the appropriate layer exponential scale and the altitude, and I set the factor of 1 here, both in the WGSL and the C++ version, then I get a complete match. So yeah, this is okay. But if I use the exponential term value here, that's where things start to get messy. How could that be? Let me try to investigate further. The funny thing here is, if we look at the definition that we have in the get earth threads, when it comes to setting up the density profile layer for the relay density and the me density, we see that the exponential term is set to 1, and here also is set to 1, and otherwise we have this ozone density where we have 2 layers, but here the exponential term is set to 0, and that's really the only density element that we have. So relay density is using this relay layer, me density is using the me layer, and then the absorption density is using this list of ozone density layers. So how the hell could we get something going differently if we force this exponential term to 1 instead of using layer exponential term? Good question. Let's try that again. Alright, so for the moment I'm still not quite sure how I'm going to deal with this differences. So I don't know, I'm going to probably just stop the recording of this session for now, and I will be working offline trying to figure out if there's anything else I could try to add on this test to make it work in a better way. Otherwise I need to reduce the sensitivity of the difference. We see that differences can go pretty high, up to 0.1 something. So if I set the threshold to 0.2, then we should be okay. And indeed, using this tolerance value of 0.2, I can get the unit test to pass. And from this point, I will need to take some time to try to see if I can improve again on this tolerance level. But basically it seems that the algorithm is working as expected on both sides. But yeah, those small differences in the computation is something I'm pretty used to with other algorithms. So yeah, usually it's pretty hard to remove all of this, but we'll see. Anyway, thanks for watching, and as usual, if you think there's anything unclear, or you have any question, or you need more details on anything on this topic, just let me know in the comments, and otherwise I keep going on the next unit test, which should be on another of those textures generated in the atmosphere model. So see you next time, and meanwhile, happy coding on your side. Bye bye.